So this is part 2 of chapter 7. And in part 2 of chapter 7, we already did all the reactions of the alkynes. Now we're going to see what alkynes are used for. So this is important because from now on, we're going to start looking at synthesis. So alkynes are very important compounds for synthesis. So synthesis using alkynes. Why are they interesting? Because especially the external or the terminal alkyne. So if I take, for example, a terminal alkyne like this, it's acidic. This proton right here is acidic. Why? Because if I bring a strong base, and usually alkynes react with a strong base such as Na, NH2 minus. So what NH2 minus does, takes the H, and this falls here. So we end up with CH3, C minus, Na plus NH3 gas. So this is a very good reaction because, first of all, it's driven to the right because we produce a gas that can escape. And then it produces a conjugate base. You see this base right here. This is a base, of course. And this is the acid. So this is the acid. And when it loses its proton, it becomes this base. And now on the other side, our sodium amide, this is an acid, and this is a base. And this is its conjugate acid. So you see that NH3 is the conjugate acid of NH2 minus. This is considered acid, even though we know that it's a base. So that tells us that this is a very strong base. So it's a very strong base. So this reaction works because you go from very strong base to a weak base. And why do we know that this is a very strong base? Because its conjugate acid is itself a base. So this is a very important reaction. Why? Because it produces this acetylide ion. So this is called acetylide ion. And that ion is a very good nucleophile. So we can use it to add carbons on compounds. So if I'm using synthesis, meaning I'm creating a new molecule, and if I want to add carbons on that new molecule, I can use the acetylide ion. So they're very good because they allow us to add a chain of carbons on compounds. So what I'm going to do is I'm going to show you some examples of synthesis where we use this process, okay? So the first example, and you have these things in your book, and we're talking about retrosynthesis. So we're going to do example 1. So what is this example? We want to go from HCCH, so this is acetylide, to CH3, CH2, CH2, CH. So this is considered a synthesis because we are creating a new molecule from a starting material. So that's what we call synthesis. So the question is, how do I go from acetylide to this? The book explains it to you. You kind of work backward. So you go what we call retrosynthesis. So what does that mean? You start with your product. So I'm going to show you the process of retrosynthesis. And as I do more questions, more examples, hopefully you will understand this. So I'm going to start with this molecule. And I'm going to say, okay, if I have this, how do I produce this? It looks like in here, we added this part. So we added this. So it means, it's not really, I'm sorry, we added this part. It means that we started with this. So how do I go from this substance? So basically, we need to go from HCCH to this. So what does it take to go from this to this? First of all, we need to remove the H, like we did here. And then we need to add this portion. So how does it work? If I start, so this is the retro, meaning I have to look at it backward, going from here to here, it's somehow we added to this, we had to add a CH3, CH2, CH2Br. Okay, so as we work the real way, so this is synthesis. How does the synthesis work? You start with your starting material, and we want to first remove an H. So we have to use this method. So it's Na plus, NH2 minus. So the NH2 takes the H, this opens, and now we get the acetylide ion with Na plus and NH3 gas. So NH3 gas escapes, that's very good, it gives us this. Now how do I go from this to this molecule? It shows that we have to add this part. So all we have to do is, so this is our step one, is to prepare the acetylide. And step two, I'm going to take the acetylide ion, and I'm going to add CH3, CH2, CH2Br. So now, and we see this more next in chapter 9, this bromine is a good leaving group. So the bromine takes the lone pair, and this attacks here. So what do we end up with is HC, C, CH2, CH2, CH3. So this is this example, how we go from here to here. Our first step is to remove the product, the acidic proton here from the acetylene, create the acetylide ion, and then add an alkyl group from this. So what's left here plus NABR. Now you see that NABR is very stable, this is very stable, and this is how compounds can be produced through synthesis. So this is example 1. As I go through more examples, I hope you'll understand it better. So now let's try example 2. So example 2, we want to go from HCCH to CH3, CH2. So you observe here, we want to go to the retrosynthesis, meaning we're going to work backwards, start with the product and see what happened between the product and the reactant. So my product here is CH3, CH, CH2. So what do I need to correlate it to this? In here we have 2 carbons, but we have 3 here. So somehow I have to go to CH3, C, CH. I have to add a carbon. And then from there, I can do HCCH. So basically what I'm showing here is first I have to somehow add a carbon, and then from the original substance. So what is then my synthesis step phase. The question is, how do I go from this to this, and how do I go from this to this? So let's start. Step 1. So this is my step 1. Would be that's my step 1. This is step 2. So what do we have step 1? Step 1, we went from acetylide to this. So how does it work? We have HCCH. That's what we did earlier. All we have to do is add Na, NH2 minus. So it's Na plus, NH2 minus. This grabs the H. This opens. We get the acetylide ion plus NH3 gas. Now I need to take this and add this. So basically, I shouldn't say step 1, I should say the synthesis here, step 1A, let's say, and step 1B. So I have to take now this and I want to add an additional carbon. So all I have to do is just put CH3Br. Every time you want to add an additional carbon on a chain, you need to use the acetylide and use an alkyl halide. So the process is, this takes the carbon, the bromine takes the pair, and we get our product, HCCCH3 plus NaBr. Now we have this. So how do I go from this to this? You see, it's obvious that here we have the right number of carbons, but we need hydrogens. So what is step 2, I'm sorry. How do I go from this compound, CH3, CH, to CH3, CH2? It looks like we added 2 hydrogens. So all I need to do is just add hydrogen. But if we put palladium, it will give me an alkane. So we have to go to chapter 7, part 1. This one, you need a Lindlar catalyst. So if you use a Lindlar catalyst, it stops at the alkene. We could also use the sodium. So it's Na or Li, and you use the ammonia liquid at minus 78 degrees Celsius. So this will also give us the same product. Now, if you remember, the Lindlar gives the cis, this one gives the trans, but here, since we have only one substituent, we don't have cis and trans. So as you can see, this is a synthesis. It shows how we go from acetylide to this substance, which is propene. We go to example number 3. Okay, so example 3. So here, I'm going to go from HCCH to CH3, CH3, Cl, Cl. So we can see here that we have 3 carbons versus 2. So we have to remove this hydrogen, add a carbon first, okay? So my first step, because as you see here, we go from 2 carbons to 3 carbons. So I have to add a carbon. Every time you have to add a carbon, you remove the H and you add a carbon. So our step 1 is HCCH, and to remove that H, we always use Na plus, NH2 minus. So the NH2 grabs the H, and we produce the acetylide ion, which is very stable, and NH3 gas, which will escape. Then the acetylide, now we can add another carbon to it. So step 2, we're going to take H, C, C minus, Na plus, and we need to add a carbon. So the best way is to use CH3Br. So it's always an alkyl halide. Every time you want to add carbons, you use an alkyl halide. So this goes here, this opens, and we end up with our 3-carbon compound plus NABR. But this is not our product. So now, step 3, this is the alkyne. So in terms of carbon, I have 3, but here we have 2 chlorine on the same carbon. So what added here, compared to, if I go from this to this, you can see that this carbon, the left one, added 2 hydrogen, and this one added 2 chlorine. So it looks like we're adding HCl excess. So remember, first HCl, you get CH2 double bond C, Cl, CH3. Remember, we already saw this in part 1. This takes the H and then the chloride. So H goes on one side, the chloride goes on the other through the pi complex. I didn't show all the mechanism. And then now that one, CH2, C, Cl, CH3, if we add another HCl, we already saw this in chapter 5, that it's a pi bond. So this takes the H first, so you end up with CH3, C plus, Cl, CH3, and then the Cl minus will attack here, and we get CH3, C, Cl, Cl, CH3. So that's our product. So you start to see here, if you want to add carbon, always take the acetylide, turn it into an acetylide ion. Then you can add whatever number of carbons you want to add. And then once you have that triple bond, you can do a lot of things with it. In here, we added twice HCl. So this step would be twice HCl, so we call it HCl excess. If we added once, it would be just one time. Okay, so we're going to go to example 4. You see, the more examples I do, the better you're going to get at it. So let's say example 4. So example 4, we want to start with this. Acetylene. I keep on calling it acetylide, I'm so sorry. And we're getting this. So this is acetylene, and we're getting CH3, CH, Br, CH3. So what happened here, again, we have 2 carbons, and here we have 3 carbons. So it looks like we added a carbon, and after that, we added the Br and H. So step 1, every time we want to add a carbon, we have to take the acetylene and remove the H. H, C, CH. This is acidic, remember, and NaNH2 is a good base to remove it because it's a very strong base. So it takes this H. And why is the acetylide ion stable? Remember, we did this in chapter 2. You have pi bonds, and the pi bonds are pulling, so that extra electron is really held tight on these 2 carbons. That's the reason this anion is stable. And then plus NH3 gas. That arrow means it escapes. Once we have our acetylide ion, So this is an acetylide ion. We're going to add to it another alkyl group. So step 2, you take your acetylide, and we're going to add CH3Br. Now, why would this reaction happen again? It's because the Br minus is very stable. It's more stable than this. It's less. It's a very weak base, Br minus, because here we're going to end up with HC, CCH3 plus Na plus and Br minus. Br minus is a weaker base than the acetylide, so that's why the reaction is complete. That's the reason we use this acetylide ion as a starting material, because it produces always a base that's weaker. Okay, so now we added the carbon. Now we're going to start with this. So I have H, C, C, CH3. So now we have the 3 carbons, and we want to get there. It's obvious that we added only 1 Br and H's. So if I add HBr, let's think about it. If I add HBr the first time, it will give me, just like here, the HCl. I will get CH2CBr. And then what can we do next? Once I have this, all I want is add hydrogen. So all we can do is add, we can add hydrogen in the presence of platinum. Okay, so you can do it in 2 ways. We can first turn it into an alkene. Okay, so what does it mean? It means we can add H2 with Lindlar. So what happened here? You add H2 with Lindlar, you end up with this. And now on the alkene here, we can add HBr. So remember, if I bring HBr will, this is a pi bond. Remember, the H adds on the less substituted. So we're going to end up with CH3 here, the H with these 2, and then C plus HBr. I'm sorry, HCH3. And now the Br minus will come, and then it will add here. And we end up with the product. Okay, we could also have done it the other way around. We can add HBr first, then add the hydrogen. But it's cleaner if we do it this way. Why? Because if you add HBr first, okay, like we did here, there's still a chance that it will go twice again. Even if you don't put an excess, there might be some compounds that will give you this. So to avoid getting the gem chloride there, the gem, meaning twice the bromine on the same carbon, we wanna just clean. It's cleaner if you do the Lindlar. Get an alkene and add an HBr. So this part is chapter 7. This part is chapter 6. Okay? The more we do, the better you're going to get at it. Okay, so we're going to go to example 5. So what am I going to do with example 5? I'm going to start with HCCH. And I want to get to this. CH2, CH3, CH2, CH3, H, and H. So if we compare them, see here, we only started with 2 carbons, and here we have 1, 2, 3, 4, 5, 6. So it's obvious we removed an H and added carbons on this side, and removed the other H and added carbon. Now, how many carbon we added on this side? It's almost like this is, if you look here, this part is this. And then that H is still there, the 2 H's, maybe you have to remove them. We'll see what happened. But all we know is that we had to add these twice, okay? So what do I do first? Step 1. I'm gonna start with HCCH again, Na plus, NH2 minus. So every time you want to add carbon, first you move that terminal proton to produce the acetylide ion. Now that acetylide ion now, step 2, is ready to add the alkyl group So we're going to add, in this case, it has to be CH3, CH2Br, because we want to add 2 carbons, not 1. In the previous scenario, we only needed CH3. So this takes the carbon, the bromine takes the pair, and we now added 2 carbons on the left, on the right, I'm sorry, plus NaBr. But now we want to add 2 carbons on this side, so we have to do it again. So step 3, we're going to take this now and remove this H. So I'm going to flip it, write it in this position. I'm just doing a 180 flip here. And then bring Na plus NH2 minus. Just like we did here, this will take this H, this opens. So we're creating another acetylide ion. Okay, plus NH3. And now this acetylide ion, now we are ready to add more carbons there. So this is step 4. We go CH3, CH2, C minus, Na plus. And we're going to add CH3, CH2Br. Same thing. This takes the carbon, this opens. So we're going to get CH3, CH2, C, CH2, CH3, plus NaBr. So now we have this, but you see what's the difference between this one and this one? This has a triple bond, this has a double bond. So it's obvious that we added hydrogen. So our last step, step 5, we want to add hydrogen, but we want the cis. So the one that gives you the cis is the Lindlar. So we go CH3, CH2, C triple bond C, CH2, CH3. If you add hydrogen gas in the presence of Lindlar, you end up with CH3, CH2, CH, C, CH2, CH3, H. So that would be your cis, and that's what we wanted to produce. Okay, so this is example 5. What if we wanted to produce the trans? If we wanted to produce the trans, we would do all of this the same, but when we get here, instead of putting Lindlar, we would use the ammonia, liquid ammonia in the presence of sodium and lithium. I just want to show you that if we wanted the trans, the last step here for the trans, I'm sorry, I'm going to put the cis here. For the trans, I would do CH3, CH2, C, C, CH2, CH3, and then here we would use Na or lithium, okay? And we would use NH3 liquid at minus 78 degrees Celsius, and we would get the trans. So what does it mean, the trans? I'd have H here, CH2, CH3 here, CH2, CH3 here, and H. So example 5 would be to give you the cis. Example 6 is to get the trans, you would use this step that's different. Okay? I have a few more examples. So example 6. And this is page 6. Example 6. So what do I have for 6? This one is more interesting. It's a little challenging, but it's okay. Actually, no, we're going to do very similar to what I just showed you earlier. So here's what we're going to do. We're going to start with H, C, CH, and we want to produce C, CH2, CH3, H, C, H, CH3. So you see here, we have a trans. Every time you have a trans and an alkene, it means somehow we went from an alkyne to an alkene using the sodium. So not only we know we're going to use the sodium and ammonia liquid, but in here we had 2 carbons, and here we have 1, 2, 3, 4, 5. 5 carbons. So basically, this portion right here is this. So what does it mean? It means you have to remove an H, add a methyl here, remove this H, add an ethyl. And then we do the trans part. So step 1, you take the acetylene. First step is remove the H. It's always NH2 because it's a strong base, and it removes this acetylene proton, and we end up with the acetylide ion. The NH3 gas escapes. Step 2, we're going to take the acetylide ion, and then we're going to add a CH3 here. So we just bring it as CH3Br. So what happened here, the acetylide takes the CH3 and the bromine takes the pair of electrons. So now we have this. So we already fixed this side. Now we need to add the ethyl on the other side. So we need to remove this H. So step 3, we're going to take this as our alkyne and remove the left H. So I'm going to write HC, CCH3, and I'm going to bring Na plus, NH2 minus, and this takes this, and we're going to end up with Na plus, And now we're going to attach on this side the ethyl group. Step 4. So this grabs the ethyl, the bromine takes off. Now we want to go from this to this. So the last step, we go from CH3, CH2, C, CH3 to this. The trans, if it's trans, it means we need to use sodium or lithium in the presence of liquid ammonia at minus 78 degrees Celsius. So that gives you the trans. So to go from here to here, we needed to do this 5 steps. Now we could switch these two with these. We could have added the ethyl first and then the methyl. We could have added this side and then that side. It doesn't really matter. The order here is not important, but the last step is important. This is our last step. Okay, another one. So here we're going to do example 7. So what do we have in example 7? I'm going from this to this. So if we pay attention to the number of carbons, we have the same number. So it looks like this portion right here became this. So basically, the alkyne turned into an alcohol. So what was added here, that the difference between here and here, it looks like we added 2 hydrogens on this carbon and a hydrogen and an OH on the other. So it looks like we added an H2 and water. To go from here to here, we had to add an H2 and then water. The question is, which one should we add first? We can't add water here because we saw it that if you add water to an alkyne, you get an aldehyde or a ketone. So there's no way of adding water first. So what we need to do is add hydrogen first. So here's step 1. We're going to start with the alkyne. And we need to add the hydrogen to get this. Now, we don't want to go all the way to the alkane. So if I want an alkene, I'm going to add hydrogen, and I can't use palladium with carbon. I'm going to use Lindlar. You can also use the sodium lithium, but Lindlar would give me this. So that's my first step. I have an alkene, and how do I go from an alkene to an alcohol? That's chapter 6. So step 2, we can add water to this. But if you remember chapter 6, if you add water in the presence of an acid, the H adds here, the OH adds there. But we have an OH that's terminal. So how do we go from an alkene to a terminal primary alcohol. In here, we have to do the hydroboration oxidation. So we're going to get HBH2. And if you remember, this is the Lewis acid. So this adds here, and it's called concerted mechanism, meaning it happens at the same time and on the same side, which is a syn addition. So we have an H here, an H here, C, H, H, and then BH2. So that's called hydroboration. And the next step is oxidation. So this compound with oxidation, which requires OH minus, H2O, and H2O2. So these are all the reactant. You end up with our final product, which is a CH2, CH2OH. So that's our example 7, where we didn't add carbons, but we changed an alkyne into a primary alcohol. Okay, next one is example number 8. I'm trying to check how much more I have for you. Yes, I have a few more. So let's try example 8. So what do we have here for 8? We're going to start with HCCH, and we want to transform it into this. So if you look closely, it looks like if you add water to an alkyne in hydroboration, you get an aldehyde. So we created an aldehyde. So you see this part here, should use the green to show it to you to be consistent, is this part. So we went from an alkene to an aldehyde. That is hydroboration oxidation. Okay, so you have to look at all the reaction we did in part 1. An alkyne turns into an aldehyde through hydroboration oxidation. But what else happened? We start with 2, so now we need to add here these 3 more carbons, so we have 5C, so we need to add this first. So what I'm going to do is remove this H to add these carbons, and then transform it into an aldehyde. So step 1, we want to create the acetylide ion. So HCCH, I'm going to bring Na plus and H2 minus. So this grabs the H, this opens, and we get the acetylide ion. So going to be Na plus, and then C minus CH plus NH3 gas. Then I want to add on this side a propyl. So step 2, So every time you add carbons, first is you remove the hydrogen from the terminal alkyne, and then you add an alkyl halide. So here I have Na plus CH minus, and I'm going to add CH3, CH2, CH2Br. So this takes this carbon, this gets, so now we added all the carbons we needed. So we're done with the carbon count. And of course, NaBr. So this and this have the same number of carbon. The last thing is to transform my alkyne into an aldehyde. So that's step 3. I'm going to start with this. So the first one is hydroboration. And the hydroboration here, you bring HBr2. Okay, so it's hydroboration. And it happens always in THF, that's the solvent. So the pi bond takes this, and this goes here. And remember, this is bulky, so it always sits at the end. So we have CH3, CH2, CH2, CH, double bond, C, Br2, H. I'm sorry, the arrows are completely wrong. I'm so sorry. The boron is the Lewis acid, so what should happen here, and I'm really sorry, this docks right here, and I'm going to use the red, and this thing goes on this carbon. Okay, too bad I don't have white out, but I hope you see the process. The hydrogen attached to this, and the boron attaches there. So that's the hydroboration. The second step would be oxidation. So what does that mean? We're going to add water to remove this. So CH3, CH2, CH2CH, double bond, C, Br2H. You add here OH minus, H2O2, and water. So that's called oxidation. And we're going to end up with, I don't have enough room, so I'm going to write it here. CH3, CH2, CH2, CH, and then double bond, CH, OH. Now, if you remember, this is called an enol. And every time you have an enol, the H moves here and the double bond moves here. So it's in equilibrium with this. So instead of CC double bond, you're going to end up with a CO double bond. But if you're going to make the CO, the H has to move here. So that's the product. And that's your aldehyde. So this is example 8. And as you can see, this is a perfect synthesis where we start with 2 carbon molecule to a 5 carbon molecule, and we change also the functional group. Okay, I have more examples, a few more, because more examples means better practice, more practice. Okay, so the next one, example 9. We are going to start again from acetylene to this product. So let's look closely. We can say two things. We can say that this part right here became this part. So we have the two carbons, and we have, so it looks like we added hydrogen and we added HBr. But then we have to add also this. So it's always, the first step is always add carbons first. So we added 3 carbons, so I have to remove an H here. So step 1, I'm going to remove this H. So we use same Na plus NH2 minus. And I have my acetylene. So NH2 grabs this opens, and we created the acetylide ion. So that's our step 1. Now step 2, this is ready to add the alkyl group. So Na plus, and then C minus. So the acetylide now is ready to attach CH3, CH2, CH2Br. So this goes on the carbon, the bromine opens, and we end up with the perfect number of carbon. But now, how do we go from an alkyne to this? So it's obvious that I'm going to put here step 3. Start with CH3, CH2. I can't add HBr first, because if you remember, we only need one H, one Br. If I add HBr first, it might also give me the double brominated here. So it's best to first add hydrogen first. So we just have to add once, so we can use Lindlar. So I'm going to add hydrogen gas in the presence of Lindlar. And we get CH3, CH2, CH2, CH, CH, H. Now, the last step is to add HBr. Step 4, I'm going to take my alkene now. Sorry, getting some dry throat here. Now, when we bring HBr, remember this is chapter 6. We're going to create a carbocation. So the pi bond takes H, this opens. So we end up with CH3, CH2, CH2, C, H plus, and then CH3. So this is a secondary, because if we put the H here, we end up with primary, so it doesn't work. So the H has to add on the terminal. And then the second step would be Br minus. We'll add to the secondary carbon. And we end up with the final product. By the way, this is Cairo. They didn't ask you that, but this is definitely a Cairo carbon. So, and this is a flat carbocation, so we can have the bromine attack from the bottom or the top. So in the end, you're going to end up with an R and the S, 2 of them. So that's our example 9. I have 2 more, actually 3 more. So 9, 10, So what do we have for example 10? We start with this, still acetylene, and we want to end up with this. So this is a geminal, meaning we added HBr twice, okay? So we have to think of like, okay, we have this, use the green here. So this is my 2 central carbon. So here, it looks like we added HBr twice, H and Br, and then H and Br. But also, we need to add these 2. So we need to add more carbons first, and then add excess HBr. So step 1, we're going to remove this proton and add an ethyl on this side. Then remove this one and add an ethyl. And by the way, when you do these, you do one side at a time. You don't do them all at once. So that's the reason I'm showing you step 1, step 2, step 3. So my first step is I'm going to remove one of them. You don't remove both, by the way. You always remove one at a time. So you have to show the process as one at a time. So step 1, this grabs this H. We're removing the left side. So it will be Na+, and then the acetylide ion plus NH3 gas. Step 2, we're going to add the ethyl on the left side. So this adds the ethyl. Now we're going to remove the H on the other side. Step 3. We're going to remove the proton on the right. So CH3, CH2, CH. So I'm hoping that by now you start to see the pattern, like, okay, all these compounds are great because we can remove the proton and attach carbons, and that makes the chain longer. So now we're ready to attach an ethyl on the other side. So that's my step 4. I'm taking CH3, CH2, C minus, so it's my acetylide ion. And I'm going to add CH3, CH2Br. Now, I can't repeat it enough, even though it looks like we did this first time, we did this second time. Every time you have to do it separately. You have to repeat and repeat and repeat. You can't just take a shortcut. So then, because as you can see, the molecule has changed from one step to the other, so you have to show it differently. Now, I'm going to take this and turn it to this. So, step 5, taking the carbons now are in. All we need to do is add hydrogen and bromine. So we're going to add HBr. Now to add HBr, this opens, and then the Br adds on the other side. It's an anti-addition. So it's CH3, CH2, CH, and then the Br comes on the other side. So if we want to go through the whole step, but I just want to show you that I don't have enough room, that's the reason. So the mechanism, we already did it, so please take a look at it. So the H adds on the one side, the bromine adds on the other, so it's an anti-addition. Okay, and then we're going to take this and we're going to add another HBr. So here, again, this opens. Now here we're going to produce a carbocation. It's best to produce it here because this would be tertiary. So you're going to end up with CH3, CH2, CH2. So now this H is there. And then C plus Br, CH2, CH3. And then once we bring our Br minus, the Br minus goes here, and we end up with the final product, which is CH3, CH2, CH2C, Br, Br, CH2, CH3. So this is this, but it's flipped. So that's our example number 10. Okay, I could stop here, but I have two more. Example 11. We want to go from acetylene to this. Now I like this one a lot because as you start to see, we're combining two chapters already right here. So you see here, we went from an alkyne to an epoxide. So how do we get an epoxide? We get it from an alkene. So we have to move this into an alkene and then get the epoxide. So that's previous chapter. But we also added carbons. So what we need to do is first add the carbons, then get the alkene, then get the epoxide, because an epoxide can only be formed from an alkene. And so I need to create an alkene, which is a double bond here, but I also need to add these two. So first step, we need to, the first few steps, we're going to add more carbons. Then we're going to add the hydrogen to get the alkene. Then we're going to make an epoxide. So step one, start with H, C, CH. We're going to remove the one from here. So it's NH2 minus Na plus. I'm writing it slightly differently, but that's okay. So this takes the H, this opens. So it's Na plus, C minus, CH plus NH3 gas. Then we're going to add the ethyl on this side. So step two, I'm going to take this. And then I'm going to add the ethyl, which comes in always in form of an alkyl halide, ethyl bromide. And then we get the elongated chain on the left. Now I'm ready to remove this H and add on the right. So step three, I'm going to take this. remove this H on the right, use NH2 minus, of course Na plus. So this takes this opens. Then the next step, we're going to add an ethyl on this side. There's nothing here. I don't know why I did that. So we end up with CH3, CH2, C, CH2, CH3. Sorry about that. This camera stop. And then we have NABR. So now we have all the carbons we need. So as you can see, this is a triple bond, but here we have the H's and they're on the same side. So if they're on the same side, we need to use hydrogen gas and Lindlar because it produces the cis. So step 5, I'm going to take this, CH3, CH2, C, and we're going to add H2 and Lindlar. Lindlar always produces the cis. So you can put C, H, C, H, and then CH3, CH3, CH2, CH3. That's our cis before we put the epoxide, before we get the epoxide. So how do we get to the epoxide? This is chapter 6. That's the last step. Step 6 is transforming an alkene to an epoxide. We use a peroxide. So we start with C, H, CH2, CH3. It's an oxidation. And a peroxide is an RCOOOH. It has an extra O that docks on the top. So that gives us this. By the way, this is chiral, and this is chiral. So it means the oxygen can dock on the top or on the bottom, and you're going to have the two mirror images. So that's combining the two chapters, 6 and 7. Now the last one, do I have a last one? Yes. Okay. So the last one, example 12. So example 12, we start with this. So this is different. We're not starting from acetylide, starting with this. And we end up with this. So take a look here. This is very interesting. We start with 4 carbons. We end up with 3. So far in all the previous examples, we added carbon. We didn't reduce carbon. But if we end up with 3, it means somehow we created something long and we cut it in 2 halves. So what is the reaction that gives you, that cuts and put oxygen on each end? That's ozone reaction. So somehow we need to make a 6-carbon chain and cut it with ozone, okay? So basically we want to go from 4 to 6 and then cut it somewhere. We'll see anyway. So you see, it looks like this part right here, CH3, CH2C, we can say that this is what we have, okay? Kind of. But wait a minute, it stops here. So this is our 3 carbons. This it's not included. So where did that go? So that's the reason we have to think like we added something here on this side, and then we chopped the molecule. So first step, step 1, we're going to add carbon on the other side. And then we're going to make a double bond and cut it to get this. Because to get an aldehyde from previous chapter, if you have a double bond, an ozone will cut it in two. So let's try this. So my first step would be first to remove this H. No matter what, I'm always going to have to remove an H. And again, it's Na plus NH2 minus. And then NH3 gas. Okay, now I want to add carbons on this side, and I want to make it symmetric because it's only given me something. So you see how I have here 2 carbons attached on this one? I'm going to add 2 carbons on that one. So if I go step 2, CH3, CH2, CC, I'm going to add an ethyl using an ethyl bromide. And of course, I had the Na plus here. So you remember, we can cut this, put oxygen, but we can't cut it as triple bond. We can cut it as double bond to get this. If we had a double bond here and we put ozone and we cut exactly the same thing. So it would get 2 of these. So before we cut it, we have to change it from a triple bond to a double bond. So the only way is to make it add hydrogen. So step 3, we're going to add hydrogen to this to make it an alkene. And of course, we need Lindlar Catalyst because we don't want to go all the way to the alkane. But add hydrogen with Lindlar. It's going to give me CH3, CH2, CH, C, CH2, CH3H. And then my last step is an oxidation, is to chop it off right in the middle. So I have CH3, CH2, CH, double bond C, CH2, CH3H. So we want to cut it here and dock 2 oxygens on each side. So that means you're going to use ozone at minus 78 degrees Celsius or something like that. It's ozonolysis. And when you chop it and you add the oxygen, you get exactly the same. So you're going to end up 2 of these. And you might say, hey, wait a minute, they didn't say 2. It doesn't matter. They are not giving you the stoichiometry when you do synthesis. They just tell you, you start from this, you get that, and the amount, you figure it out later. So that's how we get to this. And these are all the examples I want to show you to explain how from now on we're going to evolve into something interesting where we go to advanced kind of chemistry where we have all these syntheses. We're going to create more and bigger molecules. So that covers chapter 7, and thank you.